A man in his late 40s walks into a clinic complaining of word-finding trouble and fatigue. His fasting glucose is 92. His testosterone looks normal. His doctor tells him it's stress. But 3 biomarkers he never checked tell a different story. By the time most men notice something is wrong, the biology has been shifting for a decade. People assume dementia hits in your 70s or 80s as a sudden memory problem. That assumption is wrong. Longitudinal biomarker studies have redrawn the timeline, and the biology starts shifting long before anyone notices. Researchers mapped exactly how this unfolds in the China Cognition and Aging study, published in the New England Journal of Medicine in 2024. The research team tracked biomarker changes across nearly 2 decades before clinical diagnosis. Cerebrospinal fluid markers shifted first, as early as 18 years out. Metabolic markers began to drift next. Subtle cognitive changes appeared after that. Memory complaints showed up last, followed by diagnosis. That entire silent sequence lasts up to 18 years. Think about what that means for a man in his early 50s who feels sharp and productive. He could already be inside the preclinical window with no idea, tracking total testosterone and fasting glucose, maybe even his HbA1c. But fasting insulin, HOMA-IR, and what his brain actually does with glucose almost never appear on the standard panel. That gap is the blind spot, and it's where the earliest actionable signal lives. The central question is, what earliest signals you can measure in a routine clinical workup when the biology shifts a decade or more before diagnosis? You don't need a research lab. You need your doctor's office, your wearable, and a 10-minute test you can do at home. The answer splits into a metabolic signal, a sleep and autonomic signal, and a cognitive signal. Each one is measurable now, and together they form a checklist that turns an abstract fear into a concrete protocol. Now, here's where the mechanism gets interesting. We're talking about brain insulin resistance. People file insulin resistance under diabetes. The brain begs to differ. In Alzheimer's research, insulin resistance in the brain is now called type 3 diabetes. Neurons lose their ability to uptake glucose, which causes regional hypometabolism, tau accumulation, and synaptic dysfunction. Brain tissue literally starves while blood glucose looks fine. Here's what most doctors miss. Brain tissue feels the insulin problem before the pancreas does. JAMA Neurology published findings in 2015 linking insulin resistance in late middle-aged adults to measurably lower regional cerebral glucose metabolism. That same population showed worse memory performance. Their brains were already running low on fuel before any clinical diagnosis. JCI published findings in 2012 that go deeper. Brain insulin resistance in Alzheimer's patients links to IGF-1 resistance and IRS-1 dysregulation. These molecular pathways break down years before symptoms appear. They're measurable, and they're already in motion while you're still performing at work and hitting your numbers. In 2024, a meta-analysis tracked fasting blood glucose, fasting insulin, and HOMA-IR across multiple cohorts. The correlation with Alzheimer's disease risk was consistent and strong. The pattern is consistent across studies. Peripheral insulin resistance does more than associate with diabetes. It maps to the same brain energy failure that defines preclinical dementia. NPJ Metabolic Health and Disease confirmed this again in 2024. Their researchers showed that insulin resistance in the body attenuates cerebral glucose metabolism and impairs working memory even in otherwise healthy adults. You don't need to be diabetic for insulin resistance to starve your brain. That's why fasting insulin matters more than fasting glucose. Glucose can sit at 92 and look perfect while insulin climbs to compensate. The brain feels the effect first. Your blood panel misses it entirely unless you order the right test. A lot of men never do. The next logical question is which daily systems feed into the same risk pattern when insulin resistance starts starving the brain. Insulin resistance doesn't operate in isolation. It connects directly to another system you already track but probably misread. That system is sleep. Findings from the Framingham Heart Study appeared in Neurology in 2017, and they should have changed how we look at sleep. Each 1% reduction in REM sleep percentage correlated with about a 9% increase in dementia risk. Less REM sleep overall and longer REM latency both predicted higher incidence. Sleep architecture was already shifting years before any memory complaint. A 2025 Yale study added the structural evidence. Less time in slow wave and REM sleep correlated with smaller volumes in brain regions vulnerable to Alzheimer's disease. The sleep loss signaled structural change rather than merely reflecting symptoms. Your Oura Ring or Apple Watch can't replace a polysomnography study. The sleep staging on consumer wearables isn't perfectly accurate. But here's what your wearable is actually good for. It captures longitudinal trends that a single sleep study cannot. What matters is directional change over months, not a single bad night. 3 patterns on your wearable matter most. Deep sleep percentages drift down over quarters. MIM stability drops while resting heart rate climbs and HRV falls. MESA, the multi-ethnic study of atherosclerosis, linked lower HRV to vascular risk factors for dementia and to specific cognitive performance domains. A 2024 study in the Journal of Alzheimer's Disease found that alterations in heart rate and HRV from short-term recordings reflect autonomic dysfunction tied to neurodegeneration. They serve as potential biomarkers for mild cognitive impairment. Your wearable has months of data that could already show this pattern. Plenty of men look at their sleep score and move on. The clinically relevant signal is in the trend. If your deep sleep is drifting down and your resting heart rate is creeping up, that's not poor recovery. It's a neurological signal you should act on. That brings us to the clinical side of this. We're looking at processing speed. Processing speed is the earliest cognitive domain to decline in preclinical Alzheimer's and mild cognitive impairment. It's more sensitive than memory testing in the first decade. A 2025 longitudinal cohort study, published in PMC, tracked changes in executive functioning and processing speed, and found they predict disease progression in MCI and Alzheimer's disease. The slowing shows up before the forgetting does, and it's measurable with tools you already have access to. The Montreal Cognitive Assessment, or MoCA, is a validated 10-minute screening tool that includes processing speed subtests. Clinicians consider a score of 26 or higher normal. But the trajectory matters more than any single score. If you're dropping points year over year, that's the signal to act on, regardless of whether you're still above the threshold. You can also establish your own baseline with free online tests. Symbol-digit matching and simple reaction time tasks are validated subcomponents. Do them twice a year and watch the trend. Plenty of high-performing men would rather not know. But not knowing doesn't stop the biology.
This clinical picture is easy to dismiss. You notice slowed reaction time in traffic and tasks at work take longer to switch between. Word-finding delays creep into conversation. Men often blame stress, poor sleep, or age, and sometimes it's exactly that. But when these changes cluster with elevated fasting insulin, poor sleep architecture, and declining HRV, the picture is no longer benign. It's preclinical. You now have the metabolic signal, the sleep signal, and the cognitive signal. Here's how to order the blood work that ties them together. Standard physicals miss the early metabolic and vascular drivers of cognitive decline. These are the 5 markers to request from your physician, with the clinical targets used in preventive and longevity medicine. Start with fasting insulin plus HOMA-IR. Fasting glucose can look normal while insulin keeps climbing. HOMA-IR above 2.0 signals that brain glucose uptake has likely been compromised. Order both together. Add homocysteine next. It's a vascular risk factor that damages endothelium and correlates with cognitive decline, so target under 10 micromoles per liter. Then add hsCRP. This marker tracks systemic inflammation, and chronic low-grade inflammation feeds neurodegeneration. Target under 1.0 milligrams per liter. ApoB should be on the panel. It reflects total atherogenic particle number, which makes it a stronger predictor of cerebrovascular risk than LDL cholesterol alone. Lower particle count is better, and your exact target depends on your overall risk profile. Finish with LPA. It's genetically determined, so diet and exercise rarely move it much. But knowing your level is critical for risk stratification. Elevated LPA drives atherosclerosis independently of lifestyle. Retest annually if your numbers are stable and trending well. Retest every 6 months if any marker is approaching threshold, or if you're actively making interventions. One more marker is emerging and worth knowing about. p-tau 217 blood tests are FDA approved and directly detect Alzheimer's pathology. Availability is still limited in primary care, but they're worth asking about if your health system offers them. These 5 numbers tell you more about your 10-year cognitive risk than a standard lipid panel and glucose test combined. That's your checklist. Put it to work. The 10-year window is not a theory. It's a measured timeline mapped across nearly 2 decades. Cognitive decline framed as a silent process with measurable signals becomes a clinical checklist instead of an abstract fear. Next week we break down how to restore brain insulin sensitivity for brain glucose uptake. If this changed how you're thinking about your next blood panel, subscribe. This is what we cover every week.